Welcome back. So let us start the discussion on Master's theorem. So basically, this is a topic that is generally discussed in the data structures and algorithm, wherein we find the time complexity of certain recurrence relations. Right, time complexity of an algorithm that has a specific type of a recurrence relation. Right. So without delay, let us quickly jump into the intuition behind Master's theorem. So as you can see on the screen. That has been highlighted, it says that the following theorem can be used to determine the running time of divide and conquer algorithms. Okay, so whenever we come across some divide and conquer algorithms, right, so it is generally this Master's theorem is used, right? So whenever we come across certain divide and conquer algorithms, we try to use Master's theorem in order to find the time complexity of the algorithm. So what happens in divide and conquer algorithm is that for a given problem, first we try to find the recurrence relation for the problem, right? We try to find the recurrence relation for the problem. If the recurrence relation of that problem which you have designed is of the form Tn, that is T of n is equal to at n by b plus theta n power k log power pn. Okay, so suppose you have been given a problem and you are trying to find the recurrence relation of the problem. Once you found the recurrence relation of the problem, if your recurrence relation takes the form Tn equal to at n by b plus theta n power k log pn, given the constraints, please pay attention to the constraints because they are very important. A should be greater than or equal to 1, right? So this particular term here, A should be greater than equal to 1, okay? And this particular term B obviously should be greater than or equal to 1, right? Because this particular term B should be greater than 1, okay? So A should be greater than and equal to 1 and B should be greater than 1 and K here should be greater than equal to 0 and P is a real number, okay? So for clarification, A should be greater than equal to 1, B should be greater than 1, K should be greater than equal to 0 and P can be any real number. So basically, if this recurrence relation, if that specific recurrence relation satisfies these conditions, okay, that specific recurrence relation has these values of A, B, K and P as per this condition, and if the recurrence relation is of the form Tn equal to at n by b plus theta n power k log pn, then we can definitely apply Master's theorem in order to find the time complexity of the given algorithm. Okay, so there are three specific conditions that has to be kept in mind. This is the condition 1, this is condition 2, this is condition 3. Now what we do is, once we get the recurrence relation, we try to find out the value of A, that is what is the value of A here. From the expression you can find it. What is the value of B, what is the value of K, what is the value of P. Only if and only if all the four conditions are satisfied, we can proceed with Master's theorem. Now what is the condition? Now once you got the value of A, B, K and P as per this constraint and you see that okay, these are satisfied, we quickly jump to these conditions. Okay, but before that, what is necessary is, you can see, we evaluate what is the value of A and we also compute what is the value of B power K. Okay, so once you have the recurrence relation, then you will do a checking. What do we check? We check whether A is greater than equal to 1, B is greater than 1, K greater than equal to 0 and P is a real number or not. So if all these conditions are true, means you can proceed with Master's theorem. Now before proceeding with these conditions, what I will do is basically evaluate what is the value of A, you can get from the expression, and what is the value of B power K, because you already have B, you already have K, so you will evaluate the value of B power K. Now you will compare A and B power K. Okay, the values of A and B power K will be compared. Three possibilities are there: either A will be greater than B power K, or A will be equal to B power K, or A will be less than B power K. Alright, so there are three possibilities: either it will be greater than, or equal to, or less than. Based on the possibilities, we will further execute the corresponding expression, right? So for example, if we found that the value of A is greater than B power K, then we will directly say that the time complexity will be of this order: Tn equal to theta n to the power log A base B. Alright, but if you see that the value of A is equivalent to the value of B power K, the values are found to be equal, then again we will do three checkings. Now again we have to do a further checking. What will we check? We will now check the value of P, because you have already seen what is the value of P from the expression, right? So now we will see that whether P is greater than -1 or is equal to -1 or less than -1, right? Now whatever condition is satisfied, we will execute the corresponding expression. Now if P is found to be greater than -1, in this condition. Suppose you found that okay, a is equal to b power k, so you will get inside this condition. Now you will check what is the value of p. So if you found p is greater than -1, you will directly conclude that the time complexity of that recurrence relation or the algorithm will be theta n log a base b log p plus 1 n. Okay, this is the power, log power p plus 1 n. Similarly, if we find that okay, a is equal to b power k but p is equal to -1, then in that case the time complexity will be this. Okay, and similarly if you say that p is less than -1, the corresponding time complexity will be this. Okay, you can see that this and these are similar, but please don't conclude anything. You just have to follow the approach that I have said right now. First of all, check what is the value of a, b, k and c, p. This should be satisfied. Okay, this is the constraint that should be satisfied. Okay, they should be satisfied. Once they are satisfied, you will check what is the value of b power k and then compare the value of a with b power k as per these conditions you can see here, and you will execute the corresponding condition. Okay, I found here a is equal to b power k, so I'll get in, and again I have to see that I have to do another checking. What checking? I will check whether the value of p is greater than -1, equal to -1 or less than -1, and I will directly conclude that the time complexity is the following. Okay, one last case is the condition 3, where we will say that the value of a is less than b power k. So once you see that the value of a is less than b power k, we will directly jump into condition 3. Okay, once this condition is satisfied. But now again here we have to do a checking. What checking we will do? We will check the value of p. So if the value of p is greater than or equal to 0, then we can directly conclude that the time complexity of the expression will be this. Okay, you can just put the values of k, p, whatever you have obtained from the expression here. And if the value of p is found to be less than 0, then you can directly say that okay, the time complexity will be of order n power k. So things will become more clear with the help of an example, right? So we will directly jump into the discussion of the examples. We will discuss many examples here. So let us quickly start the examples. Okay, so here it is. So I have used 2 images. So the following images on the top right is the conditions that we discussed. Okay, so for the reference I have used them. Now what will we do is basically we know that the constraints are a should be greater than or equal to 1, b should be greater than 1, k greater than or equal to 0, and p should belong to any real number. Okay, fine. These are the constraints which should be satisfied. So all of them should be true. Picking up a simple example, problem 1. Tn equal to 3tn by 2 plus n square. So we know that the general expression basically is Tn equal to a t n by b plus theta n power k log p n, right? Isn't it? So yes, this is the expression, and the same thing I have written here, and this is the constraint. So pick up this example, Tn equal to 3. So basically you can see that if you compare this expression with this expression, if you compare this expression with, let me adjust my pen. Okay, so if you compare this expression with this expression, you will find that the value of a is 3, right? The value of b is 2, and the value of k is 2, and p is 0, because you don't have the log term here. So basically it means p is here 0. Okay, so because log 0 n is that, it will be 1, right? Fine. Now we know the next step is that check whether the constraints are satisfied. So basically a is 3, which is greater than or equal to 1, so satisfied. B is 2, which is obviously greater than 1, satisfied. K is 2, which is obviously greater than 0, satisfied. And p is 0, which is obviously a real number, satisfied. So all the conditions are satisfied. So now we will quickly check the value of a, b power k and compare them. So a here you got 3, b power k is nothing but 2 power 2, which is equal to 4. So you are comparing 3 and 4. You will find 3 is less than 4. Means a is less than b power k. So if a is less than b power k, we will directly jump into which condition? The third condition, right? Fine. Now again we have to check the value of p. So what value of p? We have value of p as 0, and we see that the first condition here, p greater than or equal to 0. So if a is less than b power k and the p is found to be greater than or equal to 0, we found here 0, right? Then we will find the time complexity as follows. Tn is equal to theta n power k log p n. So the value of k can be substituted here. You have k equal to 2, so you write n square log p n. So basically p is 0, so the whole term will become 1. So definitely the complexity is theta n square. Alright, so you can see here theta n square. This is how the complexity was derived using Master's theorem condition 3a, and we saw that how we reached condition 3a. Alright, so I hope this is clear. This is another similar example, so you can practice all these examples. The concept is quite similar. Now I will try to find out some specific cases. Suppose this case, okay, problem number 4. So here they have said that Tn is equal to 2 power n Tn by 2 plus n power n. Now the thing to note here is that when can we apply Master's theorem? Specifically, basically in this case you cannot apply Master's theorem. Why? Because you can simply see that we know that the value of a should be greater than or equal to 1, right? The value of a should be greater than or equal to 1, which means it should be a constant, right? But here you can see the term a here is 2 power n, and 2 power n is not a constant term because it is dependent on the value n, right? So this violates the Master's theorem, and hence the Master's theorem cannot be applied here, okay? Because this is violating the condition required, the essential conditions for Master's theorem, because the first condition itself says that the a should be greater than or equal to 1, but here we have 2 power n. The value of a is 2 power n, which is not a constant, and hence Master's theorem cannot be applied in this specific case. So the other problems are quite similar. You can discuss by the basic approach that I discussed right now. Okay, let us quickly find out this example. Now this is another special case. Suppose you have an example where Tn is equal to 64 Tn by 8 minus n square log n. Now you will say that okay, this is quite similar to what we discussed, right? We know that the Master's theorem expression says that Tn equal to a Tn by b plus theta n power k log Pn, alright? So this should be the condition. This is must, okay? In order to apply the Master's theorem, the recurrence relation that you are obtaining should be of this format. But you can clearly see that this problem statement 11 is not following this format, right? Because the function is not positive here. So that is why we will not apply Master's theorem in this specific case. Similarly, for this example, problem 9, Tn equal to a, right? Tn, this is b, and you can say that okay, alright, let me just erase it. Fine. So if you can just compare this expression, if you can compare this recurrence relation with the recurrence relation of Master's theorem, you will find that okay, the value of a is found to be 0.5. okay, now we know that the value of a should be always greater than or equal to 1, but the value of a here is found to be 0.5, right? So we will stop then and there, right? Because the essential constraint of the Master's theorem is not satisfied here, right? Because the value of a here is 0.5, so it is violating the required condition for Master's theorem. So we will not apply Master's theorem here also. So for finding the complexity of such recurrence relations, you have an alternate method, but we will not follow Master's theorem for these cases, okay? So we have one more last example to discuss. Suppose in this case you have this recurrence relation and you are to find what is the time complexity of this recurrence relation. So how do you find? Basically you will compare this with the general Master's theorem and then find the value of a, b, k and p. So we will get a is equal to 2, b is equal to 4, k is equal to 0.51, p is equal to 0, and you will see that all of these are satisfying the constraints, right? The 4 constraints that we discussed here. A should be greater than or equal to 1, b should be greater than 1, k should be greater than or equal to 0, p should belong to real number. So all these constraints were satisfied in this case, and we will now check the value of b power k. So what is the value of b power k? So b you have 4, k is 0.51. Now this value b power 4 power 0.51 is basically greater than the value of a. The value of a is nothing but 2 in this case, right? So you see this is a, this is b power k. So obviously the value of a here is less than this, and since it is less than this, so we will now move to which condition? A is found to be less than b power k. We will go to condition 3. Now we have to check the value of p. So the value of p here is found to be 0 because we already compared this and this expression and concluded that the value of p is 0. So if value of p is 0, we will just execute the first condition 3a, and the time complexity accordingly is theta n power k. What is the value of k here? 0.59 log pn. So basically this is, I am saying it log pn, okay, but it is not pronounced in that way, but just understand it is log power pn, okay. The value of p will be 0, so if it is 0, the whole term becomes 1. So you have nothing but 0, the theta and 0.51 in the last case, okay. So this is how we basically compute the time complexities of some specific recurrence relations that that are similar to this expression, okay, to apply Master's theorem. So I hope the discussion is clear. I have tried to discuss some examples to make it more intuitive, okay. So in case of any doubts, queries, you can always comment. So thanks for watching.